Okay, welcome back. Today we're starting a new unit. In the last unit, we studied the different types of energy. And one of the types of energy we learned about was thermal energy. Thermal energy is incredibly important to people. So we're going to dig a little deeper into it in this unit. Before we get started, there's a short clip I want to take a look at, and it's just an overview of thermal energy. Okay, this is a little overview of heat. We want to pay attention to how he mentions the uses of heat, which we learned about in the last unit, and how the particles' motion affects the states of matter and the behavior of matter itself.
Hot air ballooning, the warmth of a cozy fire, the eruption of a volcano, and life itself are all dependent upon heat. Flying high in a beautifully colored hot air balloon is possible because of heat. The gas flame is used to heat the air, which causes it to expand. It doesn't take long before the light material of the balloon can be lifted up by this expanded air. The hot air is not as dense or heavy as the cold air around it. The hot air is more active and requires more room than cold air. So much of the air is pushed out of the balloon.
Notice how he said as the air inside the balloon was heated, it expands, which means the particles, as we know, are moving faster and faster. That's part of the kinetic or particle theory. Because they're moving faster, they take up more space. As they take up more space, they push a lot of the air out of the balloon. So there's actually less air per area inside the balloon than outside the balloon. So it's almost like the balloon is kind of empty, which was what makes it lighter than the air around it, which is why it gets pushed up and it's less dense.
As a result, there is less air in the balloon than the air around it, and the balloon is buoyed upwards. A wood fire in a fireplace is an example of heat produced by burning. There are many other fuels that are used for burning, such as coal, oil, and gas.
So all of these things are storing energy as chemical potential energy, which is what we learned about in the last unit. And when they're burned, the energy conversion is from chemical energy to heat and light.
The energy is used in a variety of ways, from warming a house to generating electricity. This power plant uses the energy from a nuclear reaction to produce heat to boil water that turns to steam. The steam is then forced past the turbine blades of the generator. The blades spin and cause the generator to turn, producing electricity. Other power plants use other fuels, such as coal, to heat the water to make steam. So much of the electricity that we use on a daily basis is possible because of heat.
Notice how he reviewed the energy changes. It went from chemical energy to thermal energy into the steam. The steam went past the turbine turned the generator, and the generator made electrical energy.
Hot lava erupts and pours across the land as a result of tremendous pressure in the interior of the planet. Temperatures are so great that rock melts and flows from the mouth of a volcano. However, the most important source of heat is the sun. In fact, all life on our planet is dependent on the heat from the sun. There would be no life on Earth without solar energy. The sun's heat keeps the temperature within a range that is suitable for life as we know it. The heat energy from the sun keeps the water cycle operating. The water cycle is nature's way of maintaining fresh water for the Earth. The heat from the sun heats the water of the Earth's oceans and lakes so that it evaporates. This means the liquid water molecules move faster and change from their liquid form to a gaseous form.
Notice once again, it was the motion of the particles. As they're heated, they move faster. As they move faster, they break some of those connected bonds and they become gases and go up into the atmosphere.
As a gas, the water vapor rises into the air, leaving behind salt and other chemicals, so that the water vapor is clean and pure. As the water vapor rises and becomes cooled, it may begin to condense around dust particles and eventually return to the Earth's surface as a form of precipitation, rain or snow. So in more than one way, the energy from the sun is crucial to life on Earth.
As we recall from the last unit, temperature is the average kinetic energy of an object's atoms. So when we talk about this average, temperature doesn't depend on how much of a substance we have. We can have a small pan of boiling water and we can have a very large pan of boiling water, and they would both be at the same temperature. But we're going to discover that this is different than heat. Heat depends on how much of it there is. So there would be a whole lot more stored heat in the large pan of boiling water than the small one. Okay, so we say it's the average kinetic energy of the particles, and I underlined this in red because it's very important. Two substances can have the same average, even though there can be different amounts of them. Okay, so this really is measuring how fast the atoms are moving around. And remember when we talked about the kinetic theory, all the atoms and particles of a substance are in constant motion. And to measure temperatures, there's three temperature scales. Okay, there's Fahrenheit, which is the one that we typically use in the United States. It's a part of the standard system. It's not really used very much in the rest of the world. And there's three basic temperatures that we're going to take a look at on each of these scales. First one is absolute zero. On the Fahrenheit scale, absolute zero is at negative 460 degrees. Okay? And then on the Fahrenheit scale, water freezes at 32. So this is kind of the snow day temperature. If it's below 32, it'll probably snow. If it's above 32, it's going to rain. And then on Fahrenheit, water boils at 212. So at 211, it's water. At 212, it's boiling and making steam. Are the main difference between these two scales. Both are SI. 1 degree on each is the same. So if the temperature of something increases 1 degree Celsius, it gained as much energy as if it increased 1 degree Kelvin. So the degrees on each are both the same amount. The difference is where they put the zero. Okay. On the Celsius scale, zero is at negative 273 degrees. On the Celsius scale, we know water freezes at 0 and water boils at 100. So basically, to make a Celsius thermometer, you could stick a thermometer in ice water and put a mark where it was freezing, and then when it boils, put another mark, and then divide the thermometer into 100 equal marks. Now, when people started working with really cold temperatures, okay, they decided, well, if absolute zero is actually zero, then let's put the zero there. And then remember, the degrees are the same. So it's 273 degrees from the freezing point of water to absolute zero. So you have to come up 273 degrees. And the same thing on the Kelvin scale. And then it's another 100 degrees to boiling. So on the Kelvin scale, so it boils at 373 degrees. So from absolute zero to the freezing point of water on both scales is 273 degrees. You're just either going from 0 to positive 273 or from negative 273 to 0. And then it's another 100 degrees to where water boils. There's a short clip on the temperature scales that I want you to take a look at. Okay, we're going to take a look at the different temperature scales that are used. There's the one that's used in the imperial or standard system, which is the one that records temperatures in Fahrenheit. Then there's the one that we normally use in science and engineering and everywhere else in the world, which is Celsius. And then finally, there's the Kelvin scale, which has the same units as the Celsius scale, but the placement of absolute zero is at a different place.
The temperature scale used by scientists is called the Celsius scale. It is based on the freezing and boiling points of water.
Okay, so one of the things we said earlier in the year is the metric system, in a lot of ways, is based on the behavior of water. So the freezing point is 0. So if you were to make a thermometer from scratch, you could get a blank tube with no marks on it, stick it in some water that's right at freezing, like these ice cubes, and put a mark on the thermometer, and right there would be 0, wherever the liquid had risen to. Then you take and put it in the water that's at boiling, and where it's risen to, you mark it 100, and then split that halfway would be 50, and then half that would be 25, and you could make a thermometer from scratch just by knowing the freezing, the boiling point of water.
On this scale, the freezing point of water is 0 degrees, and the boiling point is 100 degrees. The scale is then divided into 100 equal degree markings. In America, the Fahrenheit scale is used in daily life. This scale uses 32 degrees as the freezing point of water, and 212 degrees as the boiling point of water. Americans are so used to the Fahrenheit scale that when we see temperatures given in Celsius, it seems confusing. However, most countries of the world use the Celsius scale. There is another scale called the Kelvin scale. This scale is based on absolute zero. Absolute zero would be the point at which all atomic and molecular activity would stop. There would be no kinetic energy. On the Celsius scale, absolute zero is minus 273 degrees. The units in the Kelvin scale are the same size as the units on the Celsius scale.
So notice that on the Celsius scale, absolute zero is here at negative 273. So to get up to 0, you have to raise 273 degrees, which is the same difference between absolute zero, which is at 0 on the Kelvin scale. If you go up 273 degrees, you get to the freezing point of water. And then room temperature is another 20 degrees. And then 100 degrees is 373, just like 100 degrees from 0 is 100 degrees. So each degree is the same amount, and the only difference is where the 0 is. In the Kelvin scale, the 0 is absolute 0. It's that point where if you could cool something down, the particles would stop moving.
So freezing water is 273 Kelvin, and boiling water is 373 Kelvin. There are no negative numbers on the Kelvin scale.
Kelvin is usually only used for extremely cold temperatures in laboratory settings, and researchers don't like negative numbers either, just like the rest of us. So if something warms up, let's say from negative 272 to negative 270, okay, they just want it to be a positive number. Okay. Absolute zero is the coldest possible temperature where the atomic motion stops. Okay, if the atoms ever stop moving and you took all the energy out of matter, then it would disappear and have no volume. But it's impossible to get there since the atoms are always moving, and any container that we put it in has energy. So the atoms in the container are going to absorb energy from the container itself, so we can never get them completely to absolute zero. Okay? So the container, the substance is in, always has heat to transfer, so we can never remove all the heat on Earth. And we're going to take a look at this clip where Bill Nye really takes a good look at what absolute zero is, and he has some nice examples in the clip. All right, this is a little clip where Bill Nye talks about absolute zero.
Welcome to the absolute zero hour. Now, we're not going to reach absolute zero, and it's not going to take an hour, but it's kind of a cool name, isn't it?
Okay.
Now, cool is just what I want to talk about today. See, this is a box of ice water. It's as cold as when you put ice in a soda. And here is a ball filled with air, and it's connected to a pressure gauge, an absolute pressure gauge. So the higher the pressure in the ball, the higher the gauge will read. You know, what's pressure? Well, it's like moving molecules. The faster the molecules are going, the higher the gauge will read. And the slower the molecules are going, the lower the gauge will read. Okay, I'm going to move the ball from here to here. Now in here we have dry ice. That's solid carbon dioxide mixed with a little alcohol, so it's still a liquid. Now this is colder than it is anywhere on Earth. This is colder than...
Notice that the pressure gauge is going down as the particles slow down. So as the particles slow down, they're bumping into the side splash. Their motion is decreasing, so the pressure is going down.
Than it is in Antarctica. It's colder than the South Pole. You see the molecules slow down and the gauge reads a lower number. Think of it this way. Here's the old molecule machine. Think of these plastic balls as molecules. And when the machine is going this fast, that's like ice water.
So that would be the molecules moving fast at a higher temperature.
So this is like a pressure gauge. And it reads this high when it's in the ice water. Then, when I lower it here, that's the pressure of the dry ice bath. So you see, the slower the molecules are going, the lower the pressure reading. Well, let me ask you this. Suppose there was no motion at all. Molecules completely stopped. Absolutely stopped. Well, that would be what scientists call absolute zero. It would be colder than almost anything you can imagine. And the reason is there'd be no molecular motion whatsoever.
So the molecules would completely stop moving in the substance. Now this assumes that there's nothing there to add energy to the molecules so that they would be moving. And listen to how Bill explains that.
So try this. We're going to put the ball of air of science into this special freezer. We're going to imagine that it's going to get very, very cold. Now, could we get to absolute zero? Actually, no. Absolutely no.
What?
If you called a travel agency and said, hey, take me to absolute zero, they'd have to go, we can't. You can't get there. Absolutely not. Isn't that weird? No, why is that? Think of it this way. Here's the ball of air, right? It's pretty cold. It's connected by this tube to this clamp. And this clamp is connected to the base of this refrigerator. And the refrigerator's on the table, and the table's on the floor, and the floor's in the building, and the building is on the earth. So there's always a path for heat to get from the earth, into the building, up onto the floor, up to the table, into the freezer, down this rod, into the ball of air. There's no way for the ball of air to be completely separated from some source of heat.
Because the heat can transfer by conduction from the earth to the floor, from the floor to the table, from the table to the refrigerator, and so on. And it'll conduct its way in to where you're trying to cool the thing. So there's no way to completely insulate it or separate the object you're trying to cool from some source of heat, is what he's saying.
Always a way for heat to get to the air. You can never quite get to absolute zero. You can't ever get to absolute zero. Zero. Scientists have gotten within 1,000th of a degree Celsius, but they've never gotten there, and they never will. Absolute zero. Zero is more of an idea than a real thing you can get. We can get within 1,000th of a degree, but we can't quite get there. There's no way. Absolutely no way. But the idea is kind of cool, isn't it? In fact, very cool. Thank you for watching the Absolute Zero Hour.
We're going to stop here and pick up next time and learn more about thermal energy.